We've been talking about monotonic functions. There are two types of monotonic functions. Monotonic increasing functions, where the value of the function always increases with x. So if x gets bigger and the value of the function gets bigger, it's a monotonically increasing function. If x gets bigger and the value of the function always decreases, then it's a monotonic decreasing function. Okay. Now, if the function is monotonic, then we know that the inverse function exists. Furthermore, there is the inverse function rule that tells us how to find the derivative of the inverse function. So let me just go over this in detail. We start off with this. Suppose y is a function of x. That means for each value of x, there's a unique value of y. And we're interested in knowing whether or not the inverse function exists. That is, can we write x as an inverse function of y? Does this exist? And the answer is yes, if the original function f is monotonic. Then we know the inverse function exists. Okay. Furthermore, there is a rule for finding dx dy. And the rule is simply this. So the answer to this question is yes, if the function f is monotonic. Either monotonic increasing or monotonic decreasing. And if f is monotonic, then dx dy, the derivative of x with respect to y, is just 1 over dy dx. You could, to figure out whether the inverse function exists. But that's not very rigorous. Yes, let's illustrate what you're saying. We were discussing this case right here. Y equals f of x equals x squared. Is this, Benjamin, is this function monotonic? No. Because if you just graph it, it looks like this. Its graph is a parabola. So it looks like that. In this section right here, notice the function is decreasing. As x gets bigger, y gets smaller. But in this half, for x greater than 0, it's increasing. As x gets bigger, y gets bigger. So this function is not monotonic. And as you said, you could just see that the inverse function doesn't exist by the horizontal line test. Well, you could see it this way. Y is a function of x, but if you want to say, is x a function of y, that would mean for each value of y, there would have to be a unique x. And for this value of y, there's two values of x. So therefore, in this case, x is not a function of y. Because for this value of y, there's two values of x. So while y is a function of x, x is not a function of y. So the inverse function does not exist in this case. Okay. Now, is this function f monotonic? What's the simple way to determine whether a function is monotonic or not? Okay, take its derivative, Johnny. And here, the derivative dy dx, or f prime of x, is equal to what? 2x. And what is true about this derivative? Johnny, did you want to? Huh? You let somebody else? Okay. What's true about this derivative? What's that? Okay, yes, but what's also true that's important for establishing whether or not this function is monotonic? Yes. Notice dy dx is positive for x greater than 0, but it's negative for x less than 0. So when the sign of the derivative can be positive for some values of x and negative for other values of x, that means the function's not monotonic. For the function to be monotonic, what must be true about the derivative? Yes. For the function to be monotonic, the derivative must either always be positive for all values of x, or it must always be negative for all values of x. Okay. And in this case, the derivative f prime of x sometimes positive, sometimes negative. So this function's not monotonic. And that means the inverse function does not exist. Now this procedure, Ben, is a little more rigorous than just drawing a graph like that. Okay. All right. Let me give you another example. Suppose we take this case. F of x equals 2x plus a 1/3 x cubed. Is this function monotonic? Okay, why, Ben? Okay, let's be more rigorous. What is the derivative? What is the derivative here? Right. And always positive. For all values of x, this is going to be positive. So that means this is a monotonic increasing function. You would have a little problem if we didn't have this 2x term. Then what would be the problem? Suppose I change this problem to this. But let me just finish this off. This is greater than 0 for all values of x. And that means it's a monotonic increasing function. Because see, x squared, this could be, the smallest value would be 0. But even if it's 0, this is still 2, so it's positive. For all other values of x, x squared will be positive. So you be adding 2 positive things. You would have a minor problem here if I change this to be this. Now f prime of x is what, Brittany? It's just going to be x squared, yeah. Multiply the 3 times the 1/3, you get x squared. Now, what's the problem here? Is this a monotonic increasing function? Well, it's hard to show it through the derivative test because if x equals 0, What is f prime of x? 0. So you want to show it's always positive. No, it can't ever be 0. You see what the problem would be? If f prime of x were 0, how would you find dx dy? Because dy dx would be 0, so then it would be undefined. Okay. So that's the problem where where dy dx is 0. Then dx dy wouldn't be defined there. Okay. All right. That's if you want to use this rule right here. You can't have dy dx ever being 0, because then dx dy wouldn't be defined there. Okay. Yes. Yeah, right. Right. So basically what you're saying is right, although there's this little complication. When x is 0, you don't want the derivative to be 0. Okay.